My name is Shizhuang Liang from Georgia Tech. Today I'm going to talk about protecting intellectual property in additive manufacturing systems against optical side channel attacks. This is a joint work with Professor Salman in Rutgers University and Professor Rahim Beya in Georgia Tech. Okay, so what is additive manufacturing? So additive manufacturing refers to a collection of manufacturing processes where materials are joined together layer by layer to directly make objects from designs. So additive manufacturing is gaining popularity in the industry, critical industry, such as aerospace, automobile, medicine, and construction. So for example, many aircraft companies are trying to use additive manufacturing to 3D print parts for their aircraft. As additive manufacturing gains popularity in the industry, the cyber threats on additive manufacturing systems are on the rising as well. So for example, by listening to the noise of a printing process, researchers were able to recover the printing paths of a printing process. So basically, in this case, we have the side channel attacks on the intellectual property of the additive manufacturing system. So what do we mean by intellectual property in additive manufacturing systems? In this case, intellectual property refers to any information about the object to be printed. The intellectual property can be very important because it can take a long time for a company to design something important to sell for a profit. Losing the intellectual property can result in financial loss. Intellectual property can take in many forms, like 3D designs, G-code instructions, which are directly understood by the printer. It can be the layer trajectories, so this can be easily visualized by human beings, or it can be the state variable signal. In this case, it's basically the coordinates of the print head over time. So actually, existing research focused on the acoustic side channel attack. So in this presentation, we're going to focus on the optical side channel attack. So this is actually a general threat model for our side channel attacks. So in this case, we have the G-code instructions, and then the G-code instructions are sent to the printer for execution. Various kinds of motors in the printer move according to the G-code instructions. As a result, an object is printed. At the same time, various kinds of side channel signals are emitted into the space. Sensors can be used to capture the side channel signals, and then machine learning or signal processing methods can be applied to analyze the side channel signals and try to recover the state variable signals from the side channel signals. The main difference between acoustic side channel attack and the optical side channel attack are the side channel signals, the sensors, and of course, the methods to analyze the side channel signals. So to perform optical side channel attacks, the first question is, how do you obtain the optical side channel signal in the first place? So it turns out that there are at least 3 different methods. So for example, for some of the additive manufacturing factories, there are surveillance cameras for security purposes. Some of the cameras may be connected to the internet, so it actually is possible for hackers to get into those cameras to get the video. This actually is possible as demonstrated by the existence of bottlenecks on the internet. And also, it's possible for the attacker to exercise social engineering. Maybe just the attacker manipulate a worker or maintenance guy into installing a secret camera on the ceiling. And it turns out that some of the printers actually have internal cameras for process monitoring purposes. Some of the printers, they even don't require very strong authentication for viewing the cameras. So an example is actually Ultimate 3, which is a very popular desktop 3D printer. So we actually perform the optical side channel attack by machine learning. As with any machine learning processes, we actually have 2 stages, the training stage and the testing stage. So for the training stage, the biggest challenge is actually to try to obtain the training data set. In this case, we assume that the attacker has access to a similar printer in a similar configuration. Then the attacker is able to ask the printer to go to various locations. For every single location, take a picture and use the coordinates of the print head as a label for the picture. So this process can be repeated over and over again automatically. To further diversify the training data set, we can also apply data augmentation, like various kinds of data augmentation methods. After we have the training data set, we're actually ready for the training. And then in this case, we actually use the modified version of the ResNet 5.0. The ResNet 5.0 is actually a very popular neural network for classification purposes. We actually modify ResNet 5.0 into a regressor. Instead of having 1,000 classes as the output, we have 3 numbers as the output, and they're basically the X, Y, Z coordinates of the print head. In the testing stage, we just basically take images from the video frame by frame For every single image, we put the image into the neural network. The neural network will be able to tell us the coordinates for that image. And then the coordinates over time actually form the state variable signal. This is actually the intellectual property. So in order to test our proposed optical selection attack, we actually built a test bed. And this is actually the picture of the test bed. We collected a total of 180,750 images in the training data set. This is actually the training process. The loss function here is actually defined as the average distance between the predicted location of the printhead and the actual location of the printhead in millimeters. So we can see that the training process basically converged and went very well. So we applied our optical selection attack to a variety of real printing processes. They're actually arbitrary printing processes. So the first row actually shows the ground truth trajectories for 8 different objects. And then the second row shows the recovery paths for the 8 different trajectories for 8 different objects. So you can see that overall the optical selection attack did a pretty good job. You can see the sizes are pretty much are equal to each other. And then it's not perfect. You can see some kind of warping here, it's not perfect, but good enough to identify most of the details in the printing process. What about different layers? As we mentioned before, this attack was designed for 3-dimensional recovery of the trajectory. Then you can see for different layers, we can still see that they did a pretty good job for the recovery of the trajectory. So we saw that the optical selection attack was a real concern. It can be performed for real printing processes. So we actually thought about some of the methods to protect the defend against the optical selection attack. So actually we look into the optical noise injection method. So we actually used a projector to project various kinds of images onto the printing area to make the selection attack harder. Okay, so to begin with, it's very important to understand that there's actually a limitation for the projectors. So you can have any number, any color as an input to the projector, but the projector is only able to project certain colors. So actually, the projector has a limited capability, limited power, limited gamut, the range of the color space. Let's imagine the other way. So if the projector has unlimited power, you can actually make this picture a constant color over time, and you are done with protection. So our question is given the limited capability of the projector, what's the best we can do about inputs to maximize the protection against the optical selection attack? So to answer that question, we actually look into some of the existing noise patterns. Replaying is a very popular one. Basically, replay the optical selection signal of another printing process. Or random blobs. We play large random blobs with random locations and random color. White noise. In this case, basically we just try to, for every single pixel in the projector, we just try to, sample from a random variable independently. And then you also have a full power, basically, try to get maximum power from the projector, try to blind the camera. Okay, as we will see later, those noise patterns were insufficient. So for that, we actually proposed something else, channel uniformization. So this method is actually, we try to make the image as uniform as possible, given the limited capability of the projector. So, lower the contrast and such that, it would be harder to see the details in the picture. The second method we actually considered was, state or time uniformization. So for a single pixel, the color of the pixel is a function of the state, different, locations of the printhead. And then the idea is basically to project something such that the color for different states now get close to each other as much as possible. In this case, it would be harder to infer the states based on the observation of the color at a single pixel, as well as for other pixels as well. This is actually a basic idea of the state uniformization. It's also called time uniformization because as the time passes by, the state will change. If you can make the signal constant over state, you will be able to make the signal constant over time as well. Lastly, we actually have the state randomization. This is actually the most powerful method. We have a certain state, and then we have a picture, right? Then we try to randomly select another state. And we know the picture of that state because we are the defender. We know everything about the system. Now we try to project something such that the image now looks like the target state instead of the original state. So there are actually two things happening at the same time. On the one hand, we're trying to conceal the original printhead. At the same time, we try to project the new printhead as clearly as possible. So it's a combination. Okay. Okay, so let's see some of the results. So here are the optical section attack results for the naive attacker. We apply the 7 noise injection patterns onto the printing area. The naive attacker is not aware of the injected noise, so they just proceeded with using the old neural network. It failed catastrophically. You can see that any noise pattern can almost effortlessly defeat a naive attacker. So the attacker doesn't want to give up. So an advanced attacker is like someone who is aware of the injected noise. So that advanced attacker just tries to put some images with the injected noise into the training data set and then proceed with the attack. So hoping that the neural network will be able to learn the pattern and then try to reject the noise and proceed with the attack. In this case, we have assumption here. For noise patterns with randomness, the images in the training data set actually has the same pattern, but not the exact same details. So for white noise, you have the white noise pattern, but not the exact white noise patterns in the testing data set. Let's see some of the results. So here are some of the optical tag results by the advanced attacker. So you can see the advanced attacker was able to recover the printing path for most of the noise patterns, but not this one. You can see it's very hard to infer some of the details like the number of keys in the gear. If this example doesn't convince you that a random state randomization was powerful enough to withstand the attack from the advanced attacker, this example might be better. So in this case, we're trying to recover a key, and all existing methods, existing noise patterns, they cannot withstand the advanced attacker. Only in this method, it's very hard to recognize the details of the key. So the takeaways like this. We actually proposed the optical section attack. Was successful for rate printing processes. We found that existing noise patterns, they can defend against a naive attacker, but not an advanced attacker. And finally, as a robust defense method, we actually proposed a domain-specific noise generation algorithm called state randomization. It's very powerful to defend against the advanced attacker. That's all. Thank you for listening to my presentation. I'm happy to take any question. Yeah.
Let's thank our speaker.